Johannes Kepler, who according to Wikipedia kind of looks like this, and was alive in like late 1500s to early 1600s. First off, says welcome to Earth Science. Second off, came up with three laws of planetary motion that we're going to try to unravel bits and pieces of and use those to really understand how the planets travel in orbits. Now, first things first, if you didn't finish lesson 13, where you played with the gravity toy and did a worksheet that has this diagram on it and noted some things, then stop right now, go back to lesson 13, go to the end of it, and finish that. If you haven't had a little bit of experience with that, some of this is going to sound a little foreign. Even if you did, some of it's going to sound a little foreign. But if you have at least taken a peek at that, some of what we're talking about with how planets orbit primary bodies, it'll be a little easier. Okay. Like I like to do sometimes, here's the state standards that are kind of related to what we're doing today. Most objects in the solar system are in regular and predictable motion. Like we know the moon phases, right? We know what we call it a year. We know how long it takes for us to go around the sun. Most of these things are very predictable. All the planets. In fact, how did I give you this if there weren't regular, predictable motions, repeatable motions? Are there some random things? Sure. That's the dinosaurs. These objects, and again, this is like where we're going with the whole entire unit, right? So all of that stuff, there's a ton to unpack there. That's not really a today thing. And we do have to talk a little bit today about gravity, how gravity is a thing, and it depends on the mass of two objects and the distance between them. Any two objects in this universe are gravitationally attracted to each other based on their mass and their distance. We'll get there. Next 1.1b, New York State's only, 15 years late on this. 8 planets move around the sun in nearly circular orbits. And that's going to be a key thing today. We're going to be talking about ellipses, 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 but at the end of the day, they're really close to circles. The orbit of each planet is an ellipse with the sun located at one foci. There's some vocab we got to get down. And the Earth is orbited by one moon and many satellites. Like, yeah, cool. We don't really need to digest that one too much today. So the big ones are that guy and what the classwork thing will be on, and a little bit of this guy. Okay, so let's do Kepler's three laws, and they go simple, medium, hard at the end of the day. Simple is the idea that planets travel in elliptical orbits. That said, at the end of the day, drawings like this are ridiculously out of proportion when it comes to what a planet's orbit looks like. This will be something you uncover when you do the lab. You're going to draw a couple of different ellipses and then compare them mathematically, numerically, to the eccentricities of the actual planet's orbits. And you're going to find that those are lower. Those are very, very round. So we science teachers throw these diagrams up there so that we can like make it kind of exaggerated so it's easy to pick out the features. But at the end of the day, they're so close to circular, you wouldn't be able to really tell at the with the naked eye. So the orbits are very circular, which is why they say 9 planets move around the sun in nearly circular orbits, really close. But there is this eccentricity and it does do some things, and we are going to note it. Okay. I went back and forth on whether to include the lab, like the mathematics in this lesson, and really kind of decided let's more focus on that during the lab. When you get there, you're going to see that the values go from 0 to 1. All eccentricity answers have to be between 0 and 1. It's just the nature of the math, and we can talk about that then, why it's a reality. But right now, you could just say, okay, I got that, because I guarantee that when I give you some questions, sometimes one of the choices will be like 1.673. That's out before you even look at what's going on. It's mathematically impossible to have an eccentricity outside of this range. 0 would be your perfect circle. So this little diagram here, E of 0, eccentricity of 0, is mathematically what a perfect circle is. And I know some of us know that like, oh, there's no such thing as a perfect circle. Well, we can define it like mathematically. We can say it's an ellipse with an eccentricity of 0. That is a perfect circle. Is that drawing? No. Is this drawing? Certainly not, because I'm doing it. But a value of 0 means perfect circle. So the further you go away from 0, the more eccentric it's becoming. It has a higher eccentricity. And we'll also note in the lab how to be careful with our language and say not more elliptical. That's not a thing. It's going to be ellipses that are higher in eccentricity and ellipses that are lower in eccentricity. But we're just opening the door. So there's Kepler's first law. That's it. Planets travel in elliptical orbits. Job done. Okay. Great if you remember that they're nearly circular. Kepler's second law, the semi-complicated law. I've always called his pizza law. And I don't know when this guy's German. I don't know when pizza made it to Germany. In fact, I tried to look it up just now and I couldn't figure it out. But if Kepler had pizza, this is how he would have explained it. If he got a pizza and he cut a piece for one person and said, I'm going to give you this piece of pizza right here that's done in green on this diagram. And somebody else in his class says, I also want a piece of pizza, and I don't want that person having more pizza than me. I want the same amount of pizza. So Kepler says, okay. And he cuts that other person a piece that looks like this. And he says, mathematically, you two people are getting the same amount of pizza. You're getting the same area of pizza. Is one person getting more crust? Yes. That's kind of where Kepler's second law is going to be a thing. But the amount of pizza you're getting is the same. All right, follow me on this. This may sound weird, talking about pizza. So if these two pieces of pizza were equal, then, and this is the thing, if we consider this planet's orbiter on the outside of this thing, the planet would take the same amount of time to travel along the crust of that pizza. So the time to go from A to B, notice that shorter distance right there, is the same amount of time that it takes to go from C to D. What does that tell us about the speeds? And I'm not going to answer that immediately. Think about that for a minute. What does that tell us about the speed of the planet in those two different locations? And he mathematically figured this out in the 1600s that the paths that it traveled, because of the planets going faster and slower, swept out equal areas in equal time. So again, this is why I really want to make sure that you played with that gravity toy, because you should have experimented with that and seen like the speed of the planet and how it varies. If you're seeing this for the first time here and you're confused, I don't blame you. Okay, another cool diagram, I just didn't want to take up too much space in the notes, is this one. Google Images, right? So here's how long it takes our planet to travel, or how I should say how far it goes in each month, right? So let's say there's a class of 12 pizza, 12 people. We cut this into 12 equal slices of pizza. Look at the crusts and how they vary a little bit. They're smaller over here and bigger over here. Well, again, what does that tell us about the speed of the planets? And again, please do remember that this is not to scale. Earth's orbit is much, 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 much more round than this. Okay, that's a lot. What do we really got to, okay, Mr. F, simplify this for me. I'm freaking out. Okay, over here, the planet goes slow. Over here, the planet goes fast. And if you say, oh, is that all I really got to know? Yeah, it is. You're not going to have to, like, nobody's going to say on a test, identify Kepler's second law. It's just this. With these orbits, if you're far from what we're going to call the primary body, if you're far from the sun, you go slow. If you're close to it, you go fast. And that's where we got to bring gravity into the party right here, this whole gravity idea. But we'll do that in just a few minutes. Kepler's third law, very complicated. Complicated enough that I was just going to skip it, honestly. But what the heck, it is a neat title to say the three laws of motion. The ratio of the square of an object's orbital period with the cube of the semi-major axis of its orbit is the same for all objects orbiting the same primary. Got it? Good. So what does that really mean? Planets that are far away take a longer time to orbit. That's it. Now, absolutely don't worry about that math. I put that on there to be kind of silly. This statement, planets that are far away take a longer time to orbit. Do we have to know that? Yeah, you do. But guess what? If you've been doing your work, but like before the last test, you've been working with this page 15 of the Earth Science Reference Tables, you already knew that, or you would already be able to always figure that out on a test, the way that they ask these things. Because if we look at these 8 planets, Mercury down to Neptune, as they get further and further and further away from the sun, what happens to their revolution, the amount of time it takes them to do one orbit. 88 days, 224, 365, 687, then over to 11, almost 12 years, almost 30 years. They go up, 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 up. So the further you are from the sun, the longer it takes to orbit. Kepler's third law, like mathematically related them in a ratio of the cube to the square. Don't worry about it. Further out you are, longer it takes to orbit. And again, you can always figure that out because you always have access to the Earth science reference tables. All right, break it down. What do we really got to know to make it through here? These notes are both like kind of to get ready for test questions, certainly to get ready for the lab. The thing with test questions on this, there's not a ton of them on the regions. I just did a scan to try to find some like I always do. There's not a ton, but what there is a lab practical on this course, which I'm going to mention thoroughly as we start the lab. This course is a lab practical as part of the Regents, where you're going to come in one day, you're going to sit at a station for, I believe, 8-9 minutes, do a lab activity, move to a second station, do a lab activity, move to a third station and do a lab activity. And one of them is drawing ellipses. One of them is going to be drawing these things. So though it's not on a ton of multiple choice questions, I promise that it's going to be one of the things you have to do on that lab practical. So let's break it down and say, what is it that I really got to know? First off, we're going to have to calculate the eccentricities of them. And again, I'm really going to save the math part for the lab. I'll wait until you guys have this in your own hands and you're doing it on your own ellipses that you drew. But here's the equation. The distance between foci, there's that vocab, we got to figure it out, divided by the length of major axis. That's more vocab we got to figure out. All right. So let's jump in. What do we got to do here? The sun, or any star that's being orbited, or if we're talking about the moon's orbits, the Earth. It's the thing that is being orbited, right? The moon orbits the Earth orbits the star, the sun, at the center. We call that, yes, we should note this. Should go a little smaller, so let's right here. The primary body. Thing that gets orbited. The primary body is at a special spot and mathematically in these elliptical orbits. Right there. We're going to represent it with a push pin when you do the lab. That's going to be F1. And then this other one that's a hypothetical point in space that's a little bit more complicated to understand is F2. So I should say what those are. F means what we call it is a focus. So it's focus 1, focus 2. And then the plural, we'll do that in parentheses, plural, is foci. You will hear people occasionally say foci, whatever. So focal point 1, focal point 2 are the two foci. So hey, distance between foci suddenly becomes not really so scary. Just measure from there to there with a ruler and you're going to have it. That's it. It's literally measuring that distance. That's a little harder when you're talking about like planets. Yes, we don't have the equipment for that, but since we're dealing with all of these on paper and comparing them to orbits, it's really easy. Distance between foci, measure from there to there, job done. Cool? Well, what else do we got to know then? I'm going to try using the line tool here. I don't do that very much. Pick a color I haven't picked yet, like orange. I'm going to draw a line. I guess you got to click and hold. Yep, there you go. Click and hold. That goes all the way across this shape right there. It goes through both foci. And if you do go through both foci, you've mathematically, automatically, easily, without thinking, created the longest possible line through the ellipse. If I do another line like from here to here across it, that would be shorter. This is the one longest line. Think of the seam on a football going all the way across it. That's what we're going to call the major axis. So let's write that right here, kind of in the same color. Same color-ish. Okay. The line really that goes through both foci, the length of major axis. Now, on the diagrams you do, they're almost always going to be like a dotted line. on the ones that you're going to physically construct. So you're going to fold the piece of paper. You'll see it when you get to the lab, and then it's automatically done. That's your major axis. Easy peasy. So really, don't let this get too scary. It's measure that line between the two foci, measure that line all the way across the shape, divide them, and you're good. If you're mathematically inclined, you might be able to see why the values can't be outside of the range from 0 to 1. You're always going to have a smaller number divided by a larger number. If you do that upside down and somehow have a larger number, that would be that these two foci are outside the ellipse. That's not how it works. The orbits don't work that way. Okay, almost there. Thanks for your patience. I know we're going long. What's next? I'm going to switch colors yet again. That was green. I'm going to put a decent sized dot right over here. At that point where the planet would be closest to the sun, and do it again over here at the point where the planet would be farthest from the sun. We're going to name those and say something important, but guess what? We already set it up here with Kepler's second law. So let's do the far one first. This point right here is called the aphelion. And if that's intimidating, I always say A is for away. It doesn't really look like many of the other words. If you can't pronounce it, if it's intimidating, remember A is for away. And what do we know about the aphelion that we've already covered? This is when the planet is capital letters far, actually farthest from primary body. And therefore, speed-wise, like we set up here with Kepler's pizza law, it is going slow. And again, ideally, you really shouldn't have gone this far if you didn't go back and play with that gravity toy to see that the planet would like go whipping by there and then come around and go a lot slower and then get to there and start to speed up and go whipping by there. If you see that in that thing, it just makes all of this so much easier. Don't panic if you're not a like vocab person. Oh no, I got to memorize more words. What really comes into play more, I'm not sure I've ever seen this. I'll do a scan, I'll see. I'm not sure I've ever seen this word or its counterpart on the regents, but the idea is that over here it's far, therefore slow, they pop up. Okay. And that's where this whole gravity thing that we'll unpack slowly over future lessons. Again, gravity is dependent on mass and distance. Well, since it's at the farthest distance in its orbit at this point, it's got the least effect to gravity. And according to the complications in Kepler's laws, that's going to make it travel the slowest. So it slows down, slows down, slows down until it gets there where it's going the slowest. And then as it starts to come back towards the primary body, it speeds until it gets there. That's the point where it's going the fastest. So let's name that. That point was the perihelion. A is for away, I guess P is for close. What can I tell you? This is when the planet is closest to the primary body. This is when it's fastest. I should have said slowest over here, but you'll get the point. Okay. Is that a lot? Absolutely. That's probably more than I've done in one note packet in terms of like this really dense amount of information, but we're gonna like use this as a cheat sheet. You know, you have this in Cami in your notes. We're gonna jump into a lab where you'll practice doing a bunch of this and practicing those questions. You're gonna have a classwork is the immediate thing you're gonna do right after this. You'll have a lab after that. We'll practice, and get this stuff down. But I think it's a pretty good start. Thanks for sticking with me. I know it was a long one. How far did we go? Oh, almost 20 minutes. Good gravy. Thanks, folks. Great job.